Welcome to the deep dive. Today, we're getting into something really fundamental in the software world.
We are. We're looking at the ISTQB Certified Tester Foundation level syllabus.
Now, I know syllabus might sound a bit dry, but honestly, think of this as the core blueprint for quality in software. It's the foundation for a qualification recognized everywhere.
And that international aspect is key. It means whether you're, developing software, managing projects, deep in QA.
Or maybe just curious about how software actually gets made reliably.
Exactly. Understanding these ISTQB basics gives everyone a common language, a shared way to think about testing, which honestly helps any project.
Totally agree. So our mission today, we're going to slice through the syllabus, pull out the really essential ideas, the principles, the processes, the techniques.
We want to give you those aha moments, right, without getting lost in every single detail.
Precisely. And what's cool is this isn't some static thing. It started way back, maybe 1999.
That's right.
But it keeps evolving. The current version, 4.0.1, was updated September 2024. So it's keeping up.
And that evolution, it really mirrors how fast software development itself changes. The need for solid testing just keeps growing.
So your role today is to guide us.
Yeah, I'll try to pinpoint what's most critical in here and maybe explain why these concepts actually matter day to day on real projects.
Okay, let's jump right in. Fundamentals. What is software testing, in a nutshell?
Okay, simply, it's a set of activities. Things we do to find defects, sure, but also to figure out if the software is actually, good enough.
So not just running tests.
No, definitely not. It's also about the thinking beforehand, the planning, analyzing what needs testing, designing how to test it effectively.
And what are we actually trying to achieve with all that? What are the objectives?
Good question. There are a few main goals, and they can shift a bit. Big one. Preventing defects from getting to the end user.
Makes sense.
Also, giving stakeholders the right information, data, so they can make smart decisions like, is this ready to go live?
Right. Decision support.
And building confidence. Confidence that the software does what it's supposed to do, that it meets the needs. But like I said, these goals can vary. Depends on the product, the risks, the development model, business factors, lots of things.
Okay. Now, something people often mix up. Testing versus debugging. What's the key difference?
Yeah, very common confusion. Testing finds the problem. It shows you where the software fails or where a defect might be hiding.
It spots the symptom.
Exactly. Debugging is the step after that. It's the detective work.
Yeah.
Finding the root cause of that failure in the code or design, figuring out why it happened, and then actually fixing it.
And after the fix.
Then we do confirmation testing, basically, rerunning the test to make sure the original problem is gone. And crucially, we also do regression testing.
To check if the fix broke something else.
Precisely.
Yeah.
Making sure we haven't introduced new problems. Oh, and one other thing, static testing, which we'll talk about later, is different because it finds defects by looking at the code or documents without running anything, so it doesn't cause a failure in the same way.
Got it. So we know what it is, but why is testing so necessary? Why is it critical?
Well, because we need to achieve those quality goals we just talked about.
Yeah.
And we need to do it within constraints, time, budget, the real world. Testing is fundamental to making sure we deliver something reliable and successful. It's not optional, really.
Can you break down some specific ways testing helps achieve that success?
Sure. For one, cost effectiveness.
Mm-hmm.
Finding and fixing a defect early, like in the requirement stage, is way, way cheaper than fixing it after release.
Exponentially cheaper, I've heard.
It really is. Second, testing gives us objective information about quality at different points in the lifecycle. That's vital for making on-the-go decisions.
Okay.
Third, testers often act as the voice of the user, ensuring the software meets actual needs, not just technical specs.
Right, the user advocate role.
And finally, sometimes it's just required. Legal reasons, contractual obligations, safety standards, testing is often mandatory.
You mentioned defects. Can you quickly explain the chain? Error, defect, failure, root cause.
Yeah, it usually starts with a human error. A person makes a mistake, maybe misunderstands something, types the wrong thing.
Like a slip-up in coding.
Or in writing requirements.
Yeah.
That error can then create a defect, a flaw, basically, in the code, the design, the document, whatever.
The actual bug.
Right. Now, if that defect gets executed under the right or wrong conditions, it can cause a failure. That's when the software doesn't behave as expected.
The visible problem.
Yes. And the root cause is the underlying reason why the initial error happened. Finding that is key to preventing it from happening again.
That clarifies the sequence nicely. Okay, ISTQB has these 7 core testing principles. What are they?
These are like the fundamental truths of testing. First, testing shows the presence of defects, not their absence.
Meaning finding bugs proves they exist, but not finding them doesn't prove they don't exist.
Exactly. You can never be 100% sure software is defect-free just because your tests passed. Second, exhaustive testing is impossible.
Too many combinations.
Way too many. For anything even slightly complex, you have to prioritize and be smart about what you test. Third, early testing saves time and money. We touched on this, find them early, fix them cheap.
Makes sense.
Fourth, defects cluster together. Often, most of the problems are hiding in a small number of modules, like the 80-20 rule.
The Pareto principle, right, helps focus effort.
Definitely. Fifth, the pesticide paradox. If you keep running the exact same tests, they eventually stop being effective at finding new bugs.
Like pests becoming resistant.
Kind of, yeah. You need to update and revise your tests. Sixth, testing is context dependent. How you test a game is totally different from how you test flight control software.
The approach has to fit the situation.
Absolutely. And seventh, the absence of errors fallacy. Just finding and fixing lots of bugs doesn't mean the system is useful or meets user needs. You might have tested the wrong things or built the wrong system altogether.
Those are crucial points to remember. Okay, next up, the test process itself. Activities, testware, roles. Let's start with the main activities.
Right, the process. It generally involves a few key stages. First, there's planning, figuring out goals, approach, resources.
Setting the strategy.
Yep. Then monitoring and control tracking progress, making adjustments as you go. Analysis comes next, looking at what you need to test, like requirements or user stories, to identify test conditions.
Figuring out what to test.
Exactly. Then test design. How are you going to test those conditions? Creating test cases, identifying data needs.
The how.
Then implementation, getting everything ready, writing test scripts, preparing the test environment, creating the data. Execution is, well, running the tests.
The actual doing.
And finally, completion, wrapping up, analyzing results, reporting on everything, documenting lessons learned. But remember, these aren't always perfectly linear. They often overlap, repeat. It depends on the project.
You mentioned context dependency earlier. How does the project's context really shape this process?
Oh, hugely. Think about who cares about the results of the stakeholders. What skills does the team have? What's the business domain? What technology are we using?
Budget.
Schedule. Budget, schedule, project risks, organizational policies, the development lifecycle itself, Agile, waterfall, whatever, tools available. All these things influence, how deep you test, what techniques you use, how much you automate, how you document things. Everything, really.
Okay. And testware, what exactly is that?
Testware is basically all the artifacts, all the stuff you produce and use during testing. It's the tangible output.
Like what?
Well, for planning, you got the test plan itself. Monitoring gives you progress reports. Analysis produces test conditions. Design creates test cases, test procedures, data requirements. Implementation gives you test scripts, actual test data. Even the test environment setup can be considered testware. Execution logs, completion reports. It's all testware.
And why is linking this testware back to the requirements or design so important? Traceability.
Traceability. It's super valuable. Let's just see, okay, this requirement is covered by these test cases, or this test case failed, which requirements might be affected.
So it helps with coverage analysis.
Yes, evaluating coverage. But also impact analysis. If a requirement changes, you know exactly which tests need updating. It's crucial for audits, for communicating progress, and just building confidence that you've tested what you intended to test.
Makes sense. And the roles. Who are the typical people involved?
It varies, of course, but you usually have testers, the people designing, implementing, executing tests. You might have a test manager or test lead who oversees the planning, coordination, and reporting.
And in Agile teams?
It can be more fluid. Developers often do more testing. Business analysts help to define acceptance tests. The lines can blur, aiming for that whole team responsibility for quality.
That's a perfect lead-in. Essential skills and good practices. What skills does a good tester need?
It's a mix. Definitely critical thinking. You need to analyze things objectively. Curiosity is huge, wanting to explore, to find out how things work and break.
Attention to detail.
Oh, absolutely. Spotting small inconsistencies. Good communication is vital too, explaining problems clearly, working with developers constructively. Some technical skill helps, understanding the domain helps, and teamwork. Testing is rarely a solo act.
You mentioned the whole team approach. What's the philosophy there?
It's really about shifting the mindset. Quality isn't just the tester's job piled on at the end. It's everyone's responsibility, baked in from the start. Developers, testers, product owners, designers. Everyone collaborates.
So breaking down silos.
Exactly. Better communication, shared understanding, catching issues earlier because everyone's thinking about quality. It generally leads to a better product.
Okay, last fundamental point. Independence in testing.
Yeah.
What are the different levels and the pros and cons?
Right. Independence. It's a spectrum. At one end, you have developers testing their own code, zero independence. At the other, maybe a completely separate external company does the testing, very high independence.
And in between.
You might have developers testing each other's work, or a dedicated test team within the same project or organization. Often, a mix is best.
What's the benefit of more independence?
Independent testers often bring a different perspective. They aren't burdened by the assumptions the original developer might have made. They might be more objective, better at finding certain types of defects.
But downsides?
Sure. Too much independence can lead to isolation. Communication gaps, maybe delays if testers are seen as bottlenecks. Developers might feel less responsible for quality if there's a separate testing police force. It's a balance.
Okay, moving into testing throughout the software development lifecycle. How does the way we build software change how we test it?
Fundamentally, testing have to adapt to the SDLC model being used. Think waterfall versus agile.
Very different rhythms.
Totally. In a sequential model like waterfall, you often have distinct big testing phases near the end. In iterative or agile models, testing is continuous. It happens within each short iteration alongside development.
So that impacts timing, scope.
Everything. Scope, timing, how much documentation you create, the specific techniques you favor, how much automation you rely on, even the roles and responsibilities. Agile, for instance, really pushes collaboration and automation.
Are there good practices that apply regardless of the model?
Oh, yes. Some things are always beneficial. Like for every development activity, there should be a corresponding test activity. Test levels component, integration, system, acceptance, each has its own focus, preventing gaps and overlap.
And starting early.
Absolutely. Starting test analysis and design as soon as possible, even based on draft requirements. Getting testers involved in reviewing documents early on, that's the core of Shift Left.
Okay, let's talk more about shift left. What does that look like in practice?
It's about pushing testing activities earlier in the timeline. So instead of waiting for code, testers get involved right away.
Like reviewing requirements.
Exactly. Reviewing requirements, user stories, design specs, writing test cases based on those early artifacts, building automated tests into the CI/CD pipeline so they run constantly, maybe even doing early performance or security checks where possible.
The goal being?
Catching defects much earlier. Because fixing a requirements bug is way cheaper and faster than fixing a code bug found weeks or months later. It requires a shift in process, maybe some training, but the payoff can be huge.
Another concept mentioned is retrospectives. How do they help testing?
Retrospectives are team meetings, usually at the end of an iteration or project to reflect. What went well, what didn't? What can we improve?
And testers participate.
Crucially, it's a chance to improve the whole process, including testing. Maybe the team identifies ways to make testing more efficient, or improve the quality of requirements to make them easier to test, or enhance collaboration between devs and testers. It fuels continuous improvement.
Okay, let's get specific about test levels. What are the main ones?
The syllabus usually outlines 5. First, component testing, or unit testing. Testing individual pieces like a single function or class in isolation, often done by developers.
Smallest building blocks.
Right. Then component integration testing. How do those pieces work together? Testing the interfaces between them.
Making sure they talk correctly.
Yep. Then system testing. Looking at the whole integrated system. Does it meet the requirements? Does it work end to end, both functionally and non-functionally?
The big picture.
Then system integration testing. If your system needs to interact with other external systems, this level tests those connections.
Like connecting to a payment gateway.
Exactly. And finally, acceptance testing. This is often about user validation. Does it meet the business needs? Is it acceptable to the customer or users? Could be user acceptance testing, UAT, operational testing, etc. Each level has different goals, uses different inputs, involves different people.
And alongside levels, we have test types. What are the main categories there?
Test types focus on what quality aspect we're evaluating. The big split is functional versus non-functional.
Functional is what it does.
Right. Does it perform the functions described in the requirements? Calculate the right values, save the right data. Non-functional is how well it does things.
Like performance, security.
Exactly. Performance, usability, reliability, security. The ISO 25010 standard lists a whole bunch of these quality characteristics. Then we also have confirmation testing.
Making sure a fix worked.
Yes, retesting after a bug fix. And regression testing, making sure that fix or any other change didn't break existing functionality. Super important.
Absolutely. Finally, for this section, maintenance testing. What triggers that?
Maintenance testing kicks in after the software is live. It's triggered by changes. Could be modifications, fixing bugs found in production, adding small features. Could be migrations, moving to a new server, upgrading the database, or even retirement testing data archiving processes, for example.
And regression is key here, too.
Always. Whenever you change live software, you need to test the change itself and then run regression tests to ensure you haven't destabilized the system. Impact analysis is crucial here too, figuring out what could be affected by the change.
Okay, shifting gears to static testing. You mentioned this earlier, testing without running the code. How does it compare to dynamic testing?
They're complementary. Dynamic testing executes the code, finds failures. Static testing examines the work products themselves, the code, requirements, designs to find defects directly. Think reviews, walkthroughs, or using automated analysis tools.
So you can find different kinds of problems.
Exactly. Static testing is great for finding issues early, like ambiguities in requirements or deviations from coding standards, often before they even become executable bugs. Dynamic testing is needed to see how the system actually behaves under execution. You really need both.
What sorts of things can we examine with static testing?
Pretty much anything created during development. Requirement specifications, user stories, design documents, architecture diagrams, the source code itself, test plans, test cases, even user manuals.
And the main benefits.
Early defect detection is the big one. Finding problems in requirements or design is much cheaper than finding them in code later. It improves development productivity because you fix things before they cause bigger issues. And it improves the quality of the documentation itself, making it clearer and more consistent.
Reviews are a big part of manual static testing. What are the usual steps in a review process?
A formal review process generally follows a few stages. Planning. Define the scope, objectives, roles, entry-exit criteria, initiation. Distribute the documents, make sure everyone's ready. Individual review. Each reviewer examines the work product on their own, noting potential defects.
And they discuss.
Often, yes. There might be a review meeting to discuss findings, make decisions. Finally, fixing and reporting. The author addresses the agreed-upon defects, and the review leader summarizes the results.
Who are the key players in a review?
Typically, you have the author who creates the thing being reviewed, reviewers, the people examining it, a review leader or moderator who facilitates the process, and sometimes a scribe who records the findings and decisions, especially more formal reviews.
Are there different kinds of reviews?
Yes, they range in formality. You have informal reviews, just a quick check by a colleague, walkthroughs often led by the author to explain the document and gather feedback. Technical reviews more formal, focused on technical correctness, often peer-led, and inspections the most formal type, very structured, focused purely on defect finding, often using checklists and metrics.
What makes a review successful? What helps it actually work well?
Several things. Clear objectives, what are we trying to achieve? Using the right review type for the goal. Keeping the material manageable, don't try to review a 500-page document in one go.
Break it down.
Definitely. Give people enough time to prepare properly. Ensure there's management support. Reviews take time. Foster a culture where reviews are seen as helpful, not judgmental. Provide training on the process. And if you have meetings, good facilitations helps keep them on track.
Okay, moving on to test analysis and design. This feels like where the rubber meets the road in terms of creating tests. How are test techniques categorized?
They help us systematically choose what to test and how. The syllabus groups them into three main buckets: black box, white box, and experience-based.
Black box is testing from the outside.
Yes, looking at the specification, what it's supposed to do without knowing the internal code structure. White box looks inside the code, and experience-based relies on the tester's knowledge and intuition.
Let's start with black box, equivalence partitioning.
Right. This is about dividing all possible inputs into groups or partitions, where you expect the system to behave the same way. For example, if a field accepts ages 1865, you have partitions. Below 18, invalid; 1865, valid; and above 65, invalid.
And you test one value from each.
Exactly. Pick one representative from each partition, like 17, 30, and 66. The idea is, if 30 works, probably 31 and 45 will too. It reduces the number of tests needed while still covering the different behaviors. It's important to test invalid partitions individually to see error handling.
And boundary value analysis, BVA, how does that relate?
BVA focuses on the edges of those partitions. Experience tells us that's where bugs often hide. So for our 1865 example, you'd test the boundaries themselves, 1865, and values just outside, 1766. Sometimes you also test just inside, 1964. It complements partitioning.
Okay. Decision table testing. When is that useful?
That's great for situations with complex business rules, where different combinations of conditions lead to different outcomes. You create a table listing all the input conditions and the resulting actions. Each column effectively becomes a test case, ensuring you cover the different logical combinations systematically.
And state transition testing.
Use this when the system's behavior depends on its past history or current state. Think of an ATM. Its behavior depends on whether you've inserted a card, entered a PIN, etc. You model the system's states and the transitions between them caused by events. Tests are designed to exercise these transitions and states.
Got it. Now switching to white box techniques. Statement and branch testing.
These look inside the code. Statement testing aims to execute every executable line of code at least once. Branch testing is stronger. It aims to execute every possible outcome of each decision point, like each branch of an if statement, true and false, at least once.
Why do this?
It helps measure how thoroughly the code structure itself has been exercised, giving confidence that you haven't missed testing some logic path. Black box testing alone can't guarantee this level of code coverage.
Makes sense. Now, experience-based techniques. How does a tester's knowledge guide these?
These rely heavily on the tester's skill and intuition. Three main ones are error guessing, exploratory testing, and checklist-based testing.
Error guessing sounds intuitive.
It is. Testers use their experience, knowledge of common mistakes, and understanding of the system to predict where errors might occur. Then they design tests specifically to target those suspected weak spots. It can be very effective.
And exploratory testing.
This is less scripted. The tester simultaneously learns about the system, designs tests based on that learning, and executes them. It's very dynamic and interactive, often done in focused time-box sessions using test charters to provide some direction, but allowing freedom to explore.
Finally, checklist-based testing.
Here, testers use a pre-prepared list of items to check or conditions to test. The checklist might come from past experience, common failure types, or specific requirements. It provides structure and ensures certain common areas are covered, but needs to be kept relevant.
Okay, the last set of approaches. Collaboration-based. How are these different?
The focus here shifts slightly. While other techniques aim to find defects, these collaborative approaches aim to prevent defects in the first place by improving understanding and teamwork, especially around requirements.
Like collaborative user story writing.
Exactly. In Agile, the whole team, devs, testers, POs, works together to write and refine user stories. Testers bring the "how will we test this" perspective early on. This helps ensure stories are clear, unambiguous, and actually testable. They often use criteria like invest independent, negotiable, valuable, estimable, small, testable.
And acceptance criteria fit in here.
Yes. Acceptance criteria are the conditions a story must meet to be considered done. They're defined collaboratively and act as concrete examples. They might be simple checklists or structured scenarios like the given when then format used in BDD, behavior-driven development. Clear criteria mean everyone's on the same page about what success looks like.
And acceptance test-driven development, ATDD.
This takes it a step further. In ATDD, you write the acceptance tests before writing the production code for a user story. Again, it's collaborative. Customers, developers, testers define these tests together.
So the tests drive the development.
Precisely. They become executable specifications. The team writes code until those predefined acceptance tests pass. It ensures the developed feature meets the agreed-upon criteria from the start. You usually start with positive tests, then add negative ones, and consider non-functional aspects too.
Right, we're moving into managing the test activities now. First up, the test plan. What's its main job?
The test plan is the central document, the blueprint for the entire testing effort for a project or release. It outlines the strategy, objectives, resources, schedule, risks. Basically, how testing will be performed and managed.
What kind of information goes in there?
Lots of things. Scope, what is and is not being tested. Objectives, assumptions, risks, the overall approach levels, types of testing, entry and exit criteria, required resources, people, tools, environments, schedule and budget, how communication will happen. It forces you to think things through.
How do testers contribute to planning in Agile, like during iteration or release planning?
They're key players. In release planning, they help analyze stories for testability, define acceptance criteria, identify quality risks, estimate testing effort, and shapes the overall test approach. In iteration planning, they break down testing tasks for the specific stories in that iteration, ensuring testing is integrated right from the start.
Entry and exit criteria, you mentioned them for the test plan. Why are they important generally?
They act as gates. Entry criteria define what needs to be true before you can start a specific test activity, like unit testing complete before starting integration testing. Exit criteria define what needs to be true before you can consider that activity finished.
Like achieving a certain coverage level.
Exactly. Or maybe all critical defects fixed. In Agile, the definition of ready for a story acts like entry criteria for development testing, and the definition of done acts as exit criteria for the story or iteration. They provide clarity and control.
Estimating test effort sounds hard. Any common techniques?
It can be tricky. Some techniques include using ratios based on past projects, for example, testing effort as a percentage of development effort, extrapolation measuring early progress and predicting the rest, wideband Delphi or planning poker getting consensus estimates from multiple experts, and three-point estimation getting optimistic, likely, and pessimistic estimates to calculate an expected value.
Once you have tests, how do you prioritize which ones to run first?
Good question, especially when time is limited. Risk-based prioritization is very common. You focus on tests covering the highest risk areas of the application first, areas most likely to fail, or where failure would be most impactful. Other factors might be requirements priority, likelihood of defects, etc.
The syllabus mentions the test pyramid and testing quadrants models. Quick overview.
Sure. The test pyramid is a model, mainly for automation, suggesting you have lots of fast, cheap unit tests at the base, fewer integration tests in the middle, and even fewer slow, expensive end-to-end UI tests at the top. Promotes catching bugs early.
And the quadrants.
The testing quadrants model, popular in Agile, categorizes tests along two axes: business-facing versus technology-facing, and supporting the team versus critiquing the product. It helps teams ensure they have a balanced mix of different types of tests serving different purposes.
Makes sense. Risk management. What are the core activities?
Two main parts: risk analysis and risk control. Analysis is about identifying potential risks, things that could go wrong, and assessing their likelihood and impact to determine the overall risk level.
And control?
Control is deciding what to do about those risks. This involves risk mitigation, taking actions to reduce the likelihood or impact, and risk monitoring, tracking the risks and the effectiveness of your controls.
What's the difference between project risks and product risks?
Project risks affect the project's success. Things like budget overruns, schedule delays, staffing problems. Product risks relate to the quality of the software itself, potential failures, security vulnerabilities, performance issues, incorrect data.
And how does analyzing those product risks influence testing?
It directly shapes the test strategy. High-risk features or quality characteristics get more attention. We might use more rigorous techniques, aim for higher coverage, dedicate more time and resources, and prioritize testing those areas. It helps focus effort where it's needed most.
What are some ways testing helps control product risk? Risk mitigation.
Yes, testing is a primary way to mitigate product risks. By finding and enabling the fixing of defects, testing directly reduces the risk of failure. Specific actions include using skilled testers, ensuring appropriate independence, conducting reviews, applying suitable techniques to achieve coverage, performing specific test types like security or performance testing, and thorough regression testing. Other controls might be accepting a risk, transferring it, or having contingency plans.
Okay, test monitoring versus test control. What's the distinction?
Monitoring is about gathering data and tracking progress against the plan. How many tests run, how many passed, failed, defects found. Control is about acting on that information, analyzing the monitoring data and making decisions, maybe changing priorities, adding resources, revising the plan to steer the testing back on course if needed.
What kind of metrics do we typically track?
A whole range. Metrics related to test progress, example, test cases planned versus executed versus passed, product quality, defect density, severity distribution, test coverage, requirements covered, code covered, risk levels, costs, and overall project progress against milestones.
And how do we communicate this? Test reports.
Yes. Test progress reports are issued periodically during testing to update stakeholders on status, findings, risks, impediments, and upcoming activities. Test completion reports summarize the entire effort at the end of a phase, evaluating overall quality, listing residual risks, and capturing lessons learned.
Are there other ways to communicate test status besides formal reports?
Absolutely. Depending on the audience and context, communication can be verbal updates and stand-ups, dashboards showing key metrics visually, emails, shared online documents, status meetings. Often a combination is best. Tailor it to who needs to know what.
How does configuration management CM help testing?
CM is vital for controlling the what and when of testing. It tracks versions of the software being tested, the testware itself, plans, cases, scripts, data, and the test environment configuration. This ensures you know exactly what was tested, with what tools, in what environment, and can reliably reproduce tests or analyze results. It manages change and maintains traceability.
Last point in this section, defect management. What's the typical life cycle of a defect?
It usually starts when a tester finds and logs a defect, providing details. Then it gets analyzed. Is it a valid defect? What's the cause? It's classified severity, priority. Then it's typically assigned for fixing. Once fixed, it's retested, confirmation. If the fix works, the defect is closed. If not, it might be reopened. This process ensures defects aren't lost and are handled systematically.
What makes a good defect report? What should be in it?
Clarity and completeness are key. You need a unique ID, a concise summary, details of the environment, OS, browser, etc., clear steps to reproduce the failure, the expected result versus the actual result, severity, impact, priority, urgency, current status, and maybe references to requirement or test cases. Enough info so someone else can understand and fix it.
Okay, final major topic, test tools. How do tools help across the different testing activities?
Tools can support almost every part of the process. Test management tools help plan, design, store tests, and track execution and defects. Static analysis tools check code without running it. Test design tools might help generate test data or cases. Execution tools automate running tests. Coverage tools measure code or requirements coverage.
Performance testing tools.
Yes, non-functional testing tools cover performance, load, security. DevOps tools often integrate testing into CI/CD pipelines. Collaboration tools help teams communicate. Environment tools like virtualization help manage test setups. There's a tool for almost everything.
Automation is a big part of that. What are the main benefits and risks?
Benefits are potentially huge. Speed, especially for regression. Consistency, repeatability, reduced manual effort, objective coverage metrics, faster feedback to developers. It can free up humans for more exploratory, thinking-intensive testing.
But the risks.
Also significant. High upfront cost and ongoing maintenance effort. Unrealistic expectations. Automation can't find every bug. Risk of automating the wrong things or automating poorly. Over-reliance, leading to neglect of valuable manual testing. Tool lock-in, compatibility issues, needing specialized skills. It requires careful planning and execution.
Wow, that was a comprehensive run-through of the ISTQB foundation level. What are the main things people should take away from all this?
I think the biggest takeaway is that professional software testing is a serious discipline. It's structured, it has principles, defined processes, specific techniques. It's not just ad hoc clicking around.
It's an engineering practice in itself.
Exactly. And understanding these fundamentals from the ISTQB syllabus provides a really solid base, a common vocabulary, whether you're a tester, developer, manager, or anyone involved in delivering quality software. It gives you a framework for thinking about and achieving quality.
Absolutely. And for listeners who thought, okay, that part was really interesting, what could they do next?
Well, dive deeper. If a specific technique like decision tables or state transition testing caught your interest, look up more examples. If Agile testing or risk-based testing resonated, explore those topics further. The official ISTQB website itself has the full syllabus and glossaries. There are tons of great books, blogs, and articles out there too, or even consider pursuing the certification itself.
Great suggestions. And finally, a thought to leave everyone with. We've talked a lot about testing software today, but think about how these core ideas, critical evaluation, risk assessment, planning for quality, looking for flaws before they cause major issues, might apply elsewhere. How could you use a testing mindset in other parts of your work or even your life? Something to ponder.
That's a great point. The principles are quite universal.
Indeed. Well, thank you for guiding us through that, and thanks to all of you for tuning in to The Deep Dive.